given by Andrew, but Andrew, as you've seen, himself in a situation to be engaged, unfortunately.
Keep going. Sorry. I lost the cursor. Okay.
And we're going to code the right? So let's thesis topic is deriving the KB algorithm for the so I thought it was very interesting for to share with you what she knows and so results. So what makes a good appearance up for fun? So one thing to remember, and many people in the field make that mistake, apparent output property, while we use radiometers to get them, are not what radiometers measure for difference. So radiance, irradiance are not radiometric. They're radiometric quantities. And in that big chart you've seen many times, they're in a separate box. So a good AOP depends weakly on external environment, as we saw with the wind, and strongly on IOP. It's basically something that we'd love to get IOP.
Until.
Yeah, and historically, IOPs were really hard to measure, and one may argue they're still hard. Because you either handle water bringing into the lab, or if your instrument goes in the water and still you're pumping it through it, you're handling the environment. While with AOPs, as you see, because we use radiometer to derive we're much less invasive in the environment. And we can also measure much bigger volumes of water than we can in other instruments. While AOPs are easier to measure using radiometers, but they are often harder to interpret. It's not simply A and B or B. It's something, some combination of things. Harder to develop an
Emmanuel,
yeah.
that's a conversation of misery.
Yes. That's first for here is it's a lot of conservation in misery. And anything that's easy to measure is hard to interpret. Hard to interpret. So it's there's no free lunch. It's always based on where we're at. And now we go to Charlotte, and I'll come back later. We're going to start talking about two AOPs, the physical information verification.
Yes.
Average.
So the diffuse attenuation coefficients are the Ks, the K functions. They're my favorite AOP, even if Kelsey disagrees, except on like a Friday night when I want to go home. Then I don't like that. So they are a bunch of them. Basically, any radiance or irradiance you can measure will have an associated K. So you have the K for the upwelling, downwelling light for the scalar light, which is we call E0. And because I'm not sure we actually talked about it before. So E0 is when you measure the light coming from all the directions, right? And it's associated with E0 downwelling, which I didn't think was very intuitive, but you're still measuring in all the directions, but the light, you're only allowing light coming down, right? But it's not planar like ED is. You still have an equal, you measure light coming in every direction from the top equally. Whereas if you're measuring ED, you're measuring it coming down, and then the strength is relative to the cosine of that light. Does that make sense? We're gonna go to it. But, and then EOU is the same thing, but for upwelling. And then there's kind of like the attention-seeking cousin, K-par, which needs a little bit more work, but we're gonna get there eventually. Okay, and Emmanuel just covered this, but ideally you would have liked to use ED or EU or any of the E's as IOP, right? AOP. But we can't. And we're going to see why in a second. But basically, for the sake of like this lecture, we're going to use these two different cases. So on the left, you have Crater Lake. It's like a glacial lake, 600-meter deep, super clean water. It's fresh water as well, glacial melt, right? So it's as close as you can get to pure water as possible. So it's a very good example of how pure water behaves and how light behaves in it. And on the right, you have St. Vicente Reservoir, which is the reservoir for drinking water in San Diego, and it's fed by the Colorado River. So it's very sediment, and you can see very well with ED, because it's easy to interpret, that like Crater Lake will be very blue because EU coming out is at a blue wavelength, whereas for San Vicente, max light is in the like brown yellowish color, right? So in theory, irradiance is great because it's easy to interpret, but the other requirement of an AOP is that they stay only vaguely dependent on external factors. And you can imagine light, if like a cloud comes through, if a cloud comes through, it's going to decrease all of a sudden, right? So it's not stable at all. Whereas an attenuation coefficient, which measures how much light changes with depth, if the cloud comes through, the light will decrease, but it'll probably decrease about the same all over the water column. So the attenuation coefficient will hopefully stay constant, which is why K functions, I can change with this, are much better contenders for IOPs. AOPs, God. I'll get there. Okay, so this is what I was saying, basically, and this is why I was asking you earlier if you tried ED with the sun. You can see the solid lines are ED or EU at different solar angles, and you can see there's a power of 10 difference, right, in between. You can also see that in between ED and EU, the slopes kind of look like they have the same slope factor. Now, if you start putting the overcast in, you have now a power of like 100, right? Even 1,000, actually, maybe. Between difference, so not good, no bueno. Whereas, if you use KDs, the solid lines are at zenith angle, which we can't really measure, but like sun coming straight down. And what you see is that it varies from what? 0.05 to 0.09. So it does vary between each KD at the surface, but it's still within the same order of magnitude, which is not at all the case here. So it's much better. What you can also see is that it seems to do something slightly different with a sun at a different angle, which means there is probably a dependence on an external factor, as in the sun angle, which is okay, as long as we can account for it and that it's not creating an extreme difference. It's still, again, in the same order of magnitude. So that's our KDs. You'll also notice, and we're going to come back to this, that at the surface, they're quite different, but at depth, they seem to converge. And this is an important property of the KDs. Boop, boop. Okay, so coming back to our two lakes, well, I don't know if that qualifies as a lake, but water bodies. Crater Lake, like I said, super clean. And you can really see that if you look at the KD of pure water, which luckily we can model very well, and the KD that is measured, you can see that they follow each other very, very well. And so does KU, which is this one, right? And with a slight difference in the blue-green regions. But this is telling you that KDs are first very much influenced by absorption, much more so than scattering, but also that they're very good. They seem to vary very well with IOPs, right? With A and BB, because if you look at the shape of KD pure water, it should remind you very much of the shape of the absorption spectrum of pure water. And then San Vicente, what you're seeing is that in that blue-green, no, sorry, in those very small wavelengths here, it's about 100 times bigger than in Crater Lake. This is due to the fact that there's a lot of sebum, there's a lot of absorption there, which means that KD or KU are very good descriptors of what is going on in that water, right? There's a lot of absorption by sebum, hence I have a very high KD. So we're on a good path. And then in the red, where there's not much that absorbs, as we just saw in the hydrolytes, it's only 2 times bigger. So yeah, the scale stops here for KD, but it's about 2 times bigger. So it's not as much influenced by what is happening, because not much is happening. That doesn't make a lot of sense, but you understand. There's not much difference because not much is happening in the red. And this is what KDs are telling us. A small note, if you go back 2 slides, you'll see they had the value of ED 0 minus, but they didn't use it here. And this again is something we'll get to in the future, but it's important to note that we tend to not use measurements right below the surface for a very specific reason.
So I think it may not happen because it's mostly water.
Yeah, it's the water that is controlling what's happening there. Sorry, there's no biological effect. Yeah. Exactly. And we talked about this actually right in your presentation, and I thought this is a graph from Colin. But it's a really nice way to understand why KDs do have this dependency on solar angle. So imagine you have this coming straight down at the zenith. KD, I've re-put the formula here, is the depth integrated ED, basically. You integrate ED over depth, and you see how much it changes. But it's, like I just said, it's integrated over depth, right? Delta Z.
Right.
But if you have an angle, the path length upon which your beam will be attenuated is not delta Z, right? This one is much longer. So if I have those 2 different beams, KD1 and KD2 defines how they're attenuated. Which one do you think will be bigger? Does anyone have an idea? There's only 2 options. And maybe 3 if you think it's the same. Okay, let's think about it. KD1.
That's the answer.
Ah. Sorry. 2. Okay. KD2, because it has more paths to do in the same light, will be attenuated more, right? Because it has to travel more. So more things will happen to this beam of light. Whereas KD1, it has a shorter path, less can happen to it, less chance of being attenuated. So what that tells you is that a larger solar angle will usually result, all other things considered even, in a larger KD. Okay, that's an important point. Now, in hydrolyte, you played a lot with C, right? Attenuation of radiance. Now we're talking about E radiance. So do you have an idea of how KD, which will detect light from a neighboring beam, and C, coming from something that only takes unscattered light, will compare? Do you think C will be higher than KD, or KD will be higher than C? So, does anyone have an idea? Yes, exactly. And this is no longer really have to do with path length, but it's just in ED, you're getting the direct light and the neighboring light that is scattered, right? So you have more light. So it's going to be attenuated more slowly because you have more, right? The level at which you will reach the same magnitude of light as when you're doing radiance will be lower. Because yeah, C has less light coming in, so for you, it'll look like it's attenuated faster. So, and because KD is how fast it's attenuated, C will always be bigger than KD, yes.
What if we have high absorption, low scattering, and a high sun angle, and get KD greater than C?
Say it again.
High absorption, low scatter, and steep sun angle, large theta, large absorption, low scatter.
So no, you won't, because even if you're not getting any scattering from the neighboring beam, you'll just turn into L, right? They'll just collect at one specific angle. So you'll just have C eventually equal to KD. You'll go closer to C, but you'll never be more. Yes,
So, the attenuation of L down is not gonna be C.
it's not gonna be what?
And you're welcome, we're welcome to do it this afternoon. If you take a radiometer measure, just radius,
Yeah,
it's not gonna be C that it's gonna be.
it has a little angle,
One is that,
yeah.
and the source is coming from every place in the surface. The beam is extremely wide. And unless, if you're outside the water, you're looking at the sun with the element. Okay, that's gonna be very close to sea. But if your sun is not if you're on the side of it, maybe you're gonna L. The only way light goes in is
True scattered light.
scatter. And as we go down, so you're collecting actually all the scatter.
So yeah, but on this diagram, yeah, I guess it's the option where it's scattered high enough above Z1 so that it comes straight down, then it's okay.
Then you're getting closer.
Within this Z1 to Z2 layer, if it gets scattered in that level, you're not gonna get in the detector, but you are gonna get into the EG detector. But it is possible indeed that it was scattered above and then came straight down. Is that what you meant?
Yeah, so if you go back up to your as much as that. So this adjustment that happened at the near the surface, that's an adjustment between absorption that tends to correlate the beam higher. Tends to bring the beam that is coming from the bottom because of this long photon gathering over percent. Scattering that tends to diffuse the light. So you have both effects happening until you get down to the top. But there's this competition between absorption and scattering. Scattering tends to diffuse the light, and absorption tends to correlate the light.
And we're gonna get there with the mean cosine.
Because you keep with absorption, it's relatively long photons that have a long path, right? So those that have high angles. While scattering tends to get something reduced. So this competition that you see more of, the angles game.
But I
Yes.
think that what she's showing in the other figure, when you have the two radiometers. I think one way to think about it,
This
I
one?
mean, I think you're going that.
Ah.
That when you're measuring, beam attenuation, you measure with an instrument that looks like a radiance. And when you're measuring absorption, you're measuring with a sensor that looks like a cosine force. And so the optical process that impacts ED is absorption, and the optical process that impacts radiance
It's attenuation.
is C. And so while it's not exactly C and A, the analogy that Charlotte is using is a really good one to think about. Does everyone understand that?
Did we confuse everyone?
Those are completely different things.
Maybe. Okay, we can go back to it. Okay, and this is quite exactly what Emmanuel was saying. Yes.
Can you go back
This one?
again?
This one?
Yes, what's done with iodide?
Yes, this is two hydrolyte simulations. You have your chlorophyll, case one, it's in the ocean optics book. I can find it.
And there's 5 different Ks, and each color is one kind of K, like two significant.
Yes,
So the difference between the angle is the difference between the curve that has a color and the one that's the same color but is.
okay. And so this is what Emmanuel was saying. Near the surface, as an AOP, like we said, KD is slightly K, all the Ks, not just KD, are influenced by their boundaries, right? So by the fact that if you look up at the sun, you'll have this collimated bead, but if you're looking down, like an upwelling KD, you won't have it. So you have different boundary conditions for each of those Ks at the surface. Now at depth, you're now no longer influenced by the fact that there are boundary conditions. You're free of them, right? If you go deep enough in the ocean, you no longer see which is up and which is down. So you no longer see the sun. And so this is called, actually, I don't know how to say it, K infinity, K asymptotic, how do you pronounce it? Asymptotic K. So it's written K infinity, we call it asymptotic K. And you can see what Emmanuel was saying, that this is a highly scattering water, so it tends to reach the asymptote very fast, because at the surface, there's all that sunlight that's being scattered in every way. And then as you go deeper, the scattered beam with longer path length will be attenuated, and you will just have the effects of the medium in which you are. Whereas in absorbing water, it will take much longer. So this is the same Y scale. It will take much longer for the Ks to converge, because you still have that collimated beam that you will see that is getting absorbed smaller and smaller, but you'll see it pretty deep, right? Whereas if you're looking down, you won't see it. So the difference between a KU and a KD will last much longer. So this is just something to be aware of. And so that tells you that at depth, once we reach that asymptotic regime, you're now completely free of boundary condition, which means you're only influenced by the IOPs. And so if you're only influenced by the IOPs, you sort of become an IOP yourself. So this is the beauty of KDs. Yes.
Question, is there any significance to like the negative diffuse attenuation?
Ah, great question. I was hoping you wouldn't notice until the end. Yes, this is, so at the surface, you can imagine that in a highly scattering medium, right below the surface, because this is for KLD and KLU, right? So they're looking up. So you could actually, if it's so scattering and it hasn't had time to be absorbed, have more light in your radiance detector than above the surface. And so more light results in a negative K. And we have a question at the end about that. So yeah, this is due to a highly scattering effect at the surface. I don't know how often that happens in real life. I don't think I've ever seen real life data with it, but it's probably in highly scattering, super pure water, super salty, that might happen. You want to say something?
Yes, that's something else, that has to do with, you said when you're down, you can't tell whether it's up and down. We can still say.
Yeah, you have the gradient, but
There
you
is
don't
still
have,
gradient.
yeah,
So when you look down, it's darker, when you look up, it is
lighter, but you don't no longer have this Snell circle of
Yes.
sun, right? And that's what the boundary condition is, the sun. All right, moving on. So now we completely understood how KDs work, right? Our Ks. And I just want to go over how we measure it. So in theory, you have this beautiful ED profile, and you will just calculate KD by doing the derivative of how much ED is attenuated over a given depth, so a delta Z. If you assume that KD is constant to depth, which we just saw is not quite true, right? It changes through depth for most of them. But if you assume that you have a large enough depth that you're considering and that you want to represent your whole layer, you can decide to make this assumption that KD doesn't change much because it moved from like 0.6 to 0.9, right? So it's an assumption you can choose to make. You then have this formula that relates the light right below the surface, this should be 0 minus KD to ED at any depth. So this looks like an easy formula, right? Easy math.
Your issue is 80 minus times the reaction.
Yes, you're right. In real life, this is a random profile I picked from Argo float measurements. And actually is a perfect example of what happens. It's not that simple. So you can see at the surface and the near surface, there's a lot of noise. Does any of you, whatever. Any idea on what might be happening there? Andrew covered it a little bit. Yeah, what happens at the surface to the light? So you're still below the surface. Yes, there's wave focusing. There can be bubbles, and they can also be a passing cloud, as we said. So you need to do something about this. And the theory is this. You have your profile, then you're gonna remove the bad points somehow. You may decide to remove the top 10 meters of your data. Like this, you're sure there's no effective wave focusing. We can talk about that's a good idea or not. So you extrapolate to the surface. Most instruments do not measure right below the surface because there's a tendency of getting out of the water. It's actually a quite difficult measurement to do. So you tend to extrapolate to right below the surface, and you can do this by doing a linear fit to the log of this data. It'll be straight. So you extrapolate to the surface, then you're going to compute the optical depth. We were just talking about it, the depth at which 90% of the light is above. So this is ED or E, 0 minus divided by an exponential. This will give you 90% of the light. And then you can find at which depth do you have this value. So now you have an idea of your optical depth. Yes. So it will vary if you're like in a stormy situation. If there is a lot of wind, there'll be more wave focusing. Yeah. Yeah, the top layer. Yeah. Yeah. So if you have a very calm lake, but we'll come to a way that we now use to quality control without having to delete your whole profile or the whole few meters. But this is like the theoretical way to do it, right? So you have your depth at which you have 90% of the light above. And thanks to math, yeah.
It's 90% at one optical depth.
Yeah.
You're losing 60% of your light, right? In terms of the satellite.
The satellite sees 90%. Yeah.
90% of the satellite
comes from that. Yeah. Yeah, I'm
But
thinking
you're
about.
looking at
Yeah, that's 67 something. Yeah. Yes, sorry, satellite wise, because we're talking about satellite applications, it's 90%, but effectively, yes, the actual math is 67%. So by the magic of math, if you have the value of 0 minus that you extrapolated, and you have your E at any depth, you can actually get a K using 1 over ZPD. That's the formula. Now, that's the theory. Now, what do you think happens to our theoretical AD0 when we're removing the first 10 meters and we're just extrapolating the rest? How do you think it is accuracy-wise? Probably not great, yes. Same with the ZPD, because then you used E0 to compute the ZPD, so you're like transmitting that error. So there are quality controls that were developed, because this is conservation of misery, right? You have a super easy map, but you have a super hard cleaning up to do. And so this is an example of the quality control that is usually done to Argo floats before calculating KDs, right? So before this whole step of going from ED to KD, you do this. So basically, like you did with the BB, you take a dart because radiometers have dart value and you need to account for that. Then you want to make sure that you have a representative sample of your data. So what we do is we need at least 5 data points in the first 10 meters. This was chosen, I don't know if there was a science reason, because you're doing a polynomial fit, so you need at least 3, but it's 5 in the literature. So you need at least 5 points in your first 10 meter, because you want to make sure that you're not actually doing this, deleting everything, and you're not actually pulling this E0 out of data at 50 meters, right? So that's not going to be good. Then you are going to remove the effect of passing cloud, which could be this, for example, or maybe this, I don't know, by doing a polynomial fit, and everything that's above 1 standard deviation, you're going to take out. And then you're going to do another polynomial fit. If it's still not good, if it still has, sorry, so you are always wanting your polynomial fit to be well correlated with your data. That's another criteria. And then you're again going to remove residuals, which are the smaller one now, which are due to wave focusing.
Sure.
Yeah.
Just go back to that one. So, just when you're talking about taking the points in the upper 10 meters.
Yeah.
This is for open ocean dealing with.
Yes, this is very case 1.
So you're looking at like a 200 meter lit zone, photic zone, right?
Yeah.
So out here, you can see a profile like this, but you're gonna be in centimeters,
Yes.
right? And
So, yeah,
it's not necessarily
let's not do that for the
centimeters.
project.
It's like it's the upper depth.
Yes.
You wanna think about. So 10 meters of the open ocean, 10 centimeters out here.
Yes.
Yeah.
So this, of course, has to be adapted. And we will have much higher resolution measure instruments than this was originally designed for Argo floats. And it will maybe have 20 measurements in the upper 50 meters because of the way it's done. So you always have to take into account when you're designing those quality controls and trying to find ways to account for all those external factors. You want to be aware of your instrument, your resolution of your instrument, and then your medium, right? What is adapted for the place you're in, right? Like you said, here we're not going to take the first 10 meters and remove everything because we won't have nothing. But this is the way it's done. And mainly the point of this was to let you know that you can't just grab at it and decide that you want a KD from this profile and it's going to be 1 line of code. You have to be careful. And this is kind of where we are now. So those are the hyperspectral trios floats that Hervé Clos lended to us. And you can see a bunch of KD, hyperspectral KDs from several locations in the world. And that's pretty exciting because before the Argo floats, which we tend to use for KDs because they have many advantages, including there's no shading by a ship, and there's a lot of them. So they have a pretty good worldwide distribution compared to like the Nomad, the cruises, where you'll have 50 points in one biome. The floats will be everywhere. So it's great when you're trying to do like inverse modeling. But they had 2 wavelengths in common with the satellites. And now those new floats, they have a lot. And in the vertical ones, you can see the wavelengths of MODIS. So already we're getting a lot more information. And once PACE is launched, we'll get even more, right? Because we'll have basically data for every point here. But that also means that we'll have to adapt our current QCs for wavelengths where the optical depth might be at 50 centimeters. So this is something to think about this is something to potentially work on. I think someone in New Labs is actually working on this. That's what you were saying, right? The new quality control, yeah. So this is exciting. And just to finish on the K function, they're super useful to try and get from satellites, because if you have the light at the surface, which RRS, the satellite sees that, and you know the K function in one specific location, you can then reconstruct the whole light field, right, under the surface, which means you know the layer in which there can be photosynthesis. You know the layer where you can constrain heat exchanges, biogeochemical processes, right? So K functions, super useful. It's always good to remember why we're doing this. Now, the cousin, K-par. Okay, so the big difference between the K reagents and the reagents and PAR is that PAR is the integrated light with that, at visible wavelengths. So it's not just at one wavelength. But do we think that all wavelengths are attenuated the same way? Those are three, again, stolen from Colin, three different PAR representation in three different waters. And we know this already, but obviously each wavelength is not attenuated with depth in the same way. So your K-par is, first of all, not going to be constant with depth, but also not going to be constant in what it means. So at the beginning, K-par is very steep because you're getting all that red out. And then K-par will become slightly smaller until the bottom. But in this K-par at 10 meters, or whatever it is, I can see the y-axis. But this K-par here doesn't represent the same thing for organisms living in the water than if I was here, right? With this, I still have red. This, I no longer have any. So even if my K values are the same, they don't mean the same thing for things in the water. So that's something to be careful of. And so you can get K-par from satellites if you want, but you have to make sure that you're calculating it in the same optical depths. And so there are formulas that exist based on other wavelengths like V490, because this is something that will be usually measured in situ and by the satellites, but this is only valid in a very specific optical depth and for very specific types of water, where we're going to assume that the spectrum of K-par attenuation is like this. So this formula, for example, will not at all be applicable here. In this water, I can see that my 490 is going to be attenuated super fast. Whereas here, it's almost one of the last wavelengths, right? So PAR, difficult, very water type dependent, and very optical depth dependent. Yes.
What kind of water body would that mean?
I actually don't know. Colin?
Well, the one at the bottom is like, oh,
Do you know what those waters are?
Yeah.
Yeah.
Not about pockets of water. The middle one are like a coastal regime where you have high organic matter, either living or dead, absorbing the and water. And then the bottom one is where you have it's like an inland water where you have really strong CDOM absorption, and so your water's looking red. So when you affect that pond or a lake in Lake Memorial Forest.
Thank you. Yeah, so if you're using PAR, or if you're using a KD-PAR algorithm, you really need to follow the guidelines and stay within the limits for which any of this was developed, whereas you have a little bit more freedom to an extent with the other codes. Okay, and then quite fast, we're going to go over another AOP, which is the average cosines or the mean cosines. At first, when I learned about this, I didn't understand what we used average cosines for. And that was my main question, because they're seldom used today. But they actually give us very good information about which way light is going, which way the radiance is going. So there are three average cosines. There's mu d, which is the downwelling irradiance over the downwelling scalar irradiance. So remember this one. And then there's mu u, which is upwelling over scalar upwelling. And then there's overall mu, which is E, directional E over scalar E, which is basically telling you if it's more coming from the top or from the bottom. So it's going to be positive in one case, negative in the other. Okay, so the best way I think is to understand how they work is with those examples. So if I have a radiance that's coming very down, it's almost downwelling, I take the average beam in a way. So it's actually going to be this one. So the theta here should stop here. But so this one, it will have a very small theta angle. And because cosine of a small number is close to 1, it'll have a large mu d. Does that make sense? Because cosine of 0 is 1. I forgot about those things. So maybe you guys know, but I tend to get confused. Okay, if we are going a little bit further, we have a large angle between our average beam and the zenith. So that results, if we do cosine of a larger angle, in a smaller mu. Okay, so part. And then if we have it going isotropically every day, like in the fog this morning, we'll have 0.5 because for mu d, let's do mu d. We have ED. So it's pretty much all of this because the average on the downwelling side, actually it's down there. The average is this one, right? If I'm looking at the downwelling one. And then I'm getting all of this measured. So it's half, right? Okay. And like I said, I didn't understand what was the point of average cosines at first. And they tell us two main things. They tell us information about if the medium is scattering or absorbing again, because, and again, this is a slide I stole from Colin. If it's more scattering, we will get that asymptotic K or mu much faster. If it's absorbing, it'll be more collimated, so that tiny beam of light that keeps going, and so it won't converge until much lower. And so in itself, this is great, but you can't get like absorption from it. But if you mix it with the K's, it becomes incredible. This is what I'm working on now. So I'll forward you the paper once it's out. Basically, we have our cosine, mu d, downwelling cosine. Be careful, we want it in seawater, so you can't use the zenith angle here. You have to do a Snell law transformation, but you guys know all of this. So we have mu d, and we know KD depends on A and BB a little bit. Now, we also know that there was this effect of the solar angle that we kind of want to get rid of. Well, we don't want to take rid of, but we want to count. And mu is the perfect way to do this, because if it's very much at zenith, this will be 1. If you are at a larger angle, you'll divide by a number smaller than 1, hence increasing your KD, which is exactly what we saw would happen because you have a longer path length. So this is actually a great way to normalize, or at least account for the dependence on the sun, and have something that hopefully fully describes the AOP, and we don't need to add any fudge factor. And one last thing, this mu d equals the cosine of the thing, the solar beam, is only valid if you have one direct light source. But you do have like the skylight irradiance, right? Like just the light emitted from the sky, not directly from the sun. So some people decided to account for it. So this is basically, we take account 60% of the cosine. So direct beam accounts for 60% of the beam coming in, and then 40% is the sky irradiance, basically. It's a little tweak to this formula, but it's important to remember that the incoming light is not just the direct beam from the sun, but also the skylight in itself. So that's something you might want to take into account if you're nitpicking a little bit. Yeah, that's it. Okay, now the question that Alex almost answered. So, what do you think is happening here? What is normal? What is not normal? Let's go with the case. Is KD normal? See, it's pretty normal. It's pretty constant. We like synthetic. We're gonna skip R because we haven't really been there. KLU and KU. What are they doing? Look at the x-axis. They're negative, right? Say mu D doing what we expect. Mu U starting to increase, which means this means that there's more light coming out, right? And negative K means you have an increase in light, which you're at 15 meters. What could be happening? And a mu U that change means that there's a change in the direction of light. Any idea yet?
What wavelength are these profiles?
I don't know. Doesn't matter.
Is hydrolite homogeneous AOPs?
Is either like what?
Is this homogeneous AOPs?
Yes, yes,
Yes.
yeah. And that's
Yes.
true agreement.
Yeah, not a 676, for example. Yes. Yes, exactly. So if you see here, ED, same downwelling going down, we expect this. But look at the radiance and the irradiance curve. They're going up. So this is because in this simulation, they've put a Lambertian bottom, so a bottom that reflects in all directions, like white sand, for example. And so this is causing some of the light to be scattered back up, affecting the Ks, affecting mu, and affecting obviously the radiance and the radiance. But yeah, does that make sense? So you can see how it's really giving you a good idea of what is happening in the medium, but at boundaries, either the top or the bottom, they'll be affected by those boundaries. So you need to be careful in analyzing them at those layers. Does that make sense?
There's like a popular formula with 15 meters, you can see similar effect to this.
Yes, you could. I think so. All right, that's all I had. Emmanuel, it's you. Yeah.
Could you just leave this slide up with the diagrams?
This one?
Yeah.
So yeah, just make sure the medium here is obviously this one. Confusing.
It's a hard act to follow, but I'll do my best.
So
What I'm gonna go through is and it's linked straight to the lab today, is reflectance.
And there are many reflectances you find in the literature, and there's many different ways to measure it. And relatively recently, Radic et al. Did for ESA kind of a survey of the methods people use today to measure reflectance. So I'll try and go with you through them. And then I want you to think throughout it about the problems that may be in the measurements. You know, what are the issues that could be associated with any one of these measures? So So in all these reflectances, what we're doing is we normalize upward lights, like coming out of the ocean, without going down towards the ocean. And this makes a lot of sense, because if you want an AOP and you don't want it to be strongly influenced by clouds, by day of the year, by time of day, if I normalize by the downward line, I'm moving the primary change, primary variable that changes with something. If the cloud is going down, if that's going down, but that's going up. So watch out for definition as I go through this survey. So what does satellite measure? Any idea here what satellite measure? When they look down to the, what is it that they're, what kind of radiometric quantities they measure? LU. So it's, but LU in what direction? So it's an upward radiant, they have a telescope. But is it, you know something about the direction of the. So most tend not to look straight down. Why would they not want to look straight down? Please, exactly. Sentinel-2 does, and this is because the physicists decided that. For completely reasons that have nothing to do with ocean color. But most sunlight will be tilted in order to avoid this. Okay, and then they have a spread around that angle. They have a swap. So each pixel will be a slightly different angle. And we know what that is. So they tend to measure off nadir, and then they normalize by a model of the plane radius. So imagine a plane radius, it's a model of ED 0 plus or 0 minus, depending on the definition of it. The model is fed with information the same satellite has collected. In satellite, we can convert the data to get information about the aerosol at that time, which we feed in order to know how much light comes in. So there's a variety of ways to do it. There's also improvement happening in delayed mode, several weeks later, by assimilating data from things like MERA-2, which are these reanalysis products of atmospheric properties based on many different satellites. It's really amazing what's happening. Because there's so many satellites that their information that they're measuring is useful for us to get a good model of what's making, a better model of the amount of light that 2 weeks ago was maybe 2 years. Because that is how much light makes it to the surface of the ocean depends on the aerosol properties, on how much humidity was in the air, on pressure, because radiation is directly related to pressure, that's how much atmosphere we have on top of it. So we want to know the pressure, because we'll get to that in the atmospheric correction. But atmospheric correction is done for the radiance, but there's also that comes into the model of the radiance. But remember, this is a model, not measurement. Satellite cannot measure on a fact. And often they will also normalize for reflectance where the sun is negative and your LU is equal. So now you're measuring it here, but you come up with some formulas to do it if you measure it here. You're looking straight down without the data, and your data is clear. And also for the sun to be clear, because they want to remove secondary effects that have to do with my viewing angle and the sun. And these are tiny details, but they will make a reflectance of satellite X different than Y, and you will not understand why. Or it's changing with the season in ways that. So these are things to think about when you download a reflectance. Did they normalize? Did they not? And you're trying also to compare to your measurement. Are my measurements similar, or in what ways are they different? The agency. So there's two sites in the world. This one unfortunately does not exist anymore. That have been used to calibrate satellites using very well characterized radiometer, particularly in Roby. And Julia works at the team that's responsible to the calibration. Not much more than I can about this. I think I'm the only person who dove in both of this. I dove on this one I skimmed it, but it's, I mean, it's really. So that's my credit today. So, but what do they measure? These all have an ED plus on top. They have a buoy on top that measures ED plus. And then they measure under the surface upwelling gradients at nadir coming in. And then they also typically also measure other things, including downwelling. So there's an ED plus on top and they measure. And these are measured at different depths. So for example, for Moby, it's 1, 5, and 9 meters. For Busol, it was 4 and 9 meters. And then they're extrapolated by feeding a K function through these measurements to the surface. Any idea as to what kind of uncertainty can happen because of that extrapolation? Variation. So yeah, so if IOPs are not if IOPs are not constants, that could be an issue. So if they have layering, but typically these are environments with open ocean, mixed layer is deeper than these sensors. For IOPs, we can assume most of the time to be constant, but you're right. The K function might vary with depth, and I'm assuming that my K function can be derived from these. But which wavelength do you think will be most problematic with this? Yes, right? Right. There's a paper from Stransky's lab looking exactly at this issue of extrapolation from 1 meter, and why is that an issue? Because there's inelastic scattering, and inelastic scattering tends to happen. Inelastic scattering happens in many wavelengths are different. And because red wavelengths are absorbed so strongly by water, it's only affecting at the surface that will be radiated out, that you will not be able to sense at 1 meter depth. So the further you go to the red, further uncertainty that it brings in terms of what is the true value of LW and spectrally coming out. So you want to make these measurements as close to the surface as you can, in order if you want to do red. Also, there's much less signal in the red because as water is strongly absorbed. So if you want to go, the further you want to go to the red, eventually you have to go out of the water. It's not really water absorption is strong. And then we have to remember that you also have to go through the interface. And typically it's done with a formula like this that has to do with the Fresnel transmission through the surface, which is closely one, but not exactly one. And then this n squared law. Yes.
So is it the inelastic scattering or is it the absorption by water? Is it both? That makes sense.
So absorption by water would decrease the signal you get. If there was not inelastic scattering, you get an uncertainty simply because your signal is better. Inelastic scattering exacerbate because it's and so you have to model it in some way because you're going to get emissions in the red that you don't sense at 1 meter, or you cannot constrain it. If you can't get close enough to sense them. So I mean, there's globin fluorescence that's going to play a role. Globin fluorescence can happen at any depth because the light that excites them go quite deep. But the emitted light is going to get absorbed very shortly close to this one. It's going to come from here, the emitted light, while here it's going to whatever is emitting there. And Raman is an emission by water. And Raman, what we know about Raman comes only from labs. I mean, we know it's important in the ocean, but it's come from labs we don't know well, it's temperature and it's salinity. And it's likely to be temperature. So there's very few data about it. So that's one of the gaps identified by the phase science stages. We need to know Raman better. Because it particularly in open ocean, the smaller, the closer, the lower the atmosphere, the more the Raman And this is the n squared law that Andrew talked about yesterday. So this is to cross the interface. And you can imagine that these are going to change with what? What will change the transmission? C6. This is a theoretical one, but it's any bias in that will affect your calculation. This is a new system that was developed for flow-based validation, where on the profiling flows of the type that you heard from on the other flow that you heard from Charlotte, there are two. Now we have two radiometers, and two give you redundancy. Not only they give you redundancy, there's something else we didn't talk about that can cause an uncertainty when you have radiometers on a structure. What else? So tilt, and tilt is one of them. So you're absolutely right. Tilt is happening in all of them. But you're monitoring that, and then you use the criteria to get data that's beyond. In soil, just to 10 degrees, in voltage, it's 2 degrees. The most of that. But what else happens? You have a radiometer here or here. What can affect shading by the structure? So cell shading is the sensor itself. So the cell itself here brings some light that will interact with just below, and then the structure itself shades. And it depends on where the sun is in the sky relative to the structure. You see, if you turn it are more towards the sun, and then have less shading in that further. You know exactly which structure it is. The shading is a factor. And one of the reasons two radiometers have been put on the antenna is to monitor that. Monitor both differences in drift between the two, but also if there's specific orientation relative to the flow, you always have one of these is outside the shade of the flow. And they're quite far. So the idea here is very similar to the other ones, except that this float, it does a profile from which you get your fluid. And then when it's near the surface, it stays in Bowdoin and measure for about 80 scans. And then those are at about 10 centimeters. So we don't have to start from 1 meter from 10 centimeters. The downside is we cannot collect as much data along the way, so our KDs and feeds to a profile that is done. We have an ES sensor here that's not hyperspectral. These two are very hyperspectral and very high resolution. The ED is not, and there's a model to get the ED plus that Robert has done, showing that actually with the 4 wavelength we have here, we can do a really good job in getting hyperspectral. Plus, but again, as I said, the satellite uses, if this is for satellite calibration and validation, the satellite uses the model. So we can use the same model with the satellite method to do the validation. Yeah. So, and this is affected by these states again, but there's, again, you still sensors to do that. The other advantage of this one is that you can deploy it anywhere in the world that you feel like. It's much more portable than a big structure. But the disadvantage is the requirement, say you want to do calibration, is that you do post-cal and pre-cal. So you have to take these, unlike Argoflows that chuck and forget, these you need to bring back to the lab and make the measurements to make sure that they did not drift and know how much they drifted if you want to do calibration level things. Here it is. Oh, yeah. Oh, that's not. I had another. Oh, it's here. Sorry, it's moved. It's sorry. I'll show you. It's here. This is me. Yeah. This is it. It's about my size in height and about 30K. This is in Crete. What? A year and a half ago. What? The box is big, yeah. It's amazing fun. So this is, yeah. It needs to be.
So there's also a set of radiometers that are profiling radiometers. Where you, and there's two kinds of those. You might have heard about it. There's the COX from biospherical, and there's the hyperprobe from Atlantic and now the Seabird. And they're kind of different approaches to the problem of waveforms. With this one, you're controlling the buoyancy of this thing. This is the upwelling irradiance, there's a downwelling radiance there. And it's very slowly in the water. As you're taking a profile, and slowly higher. I mean, actually, when we try, we bring it back. It goes to our profile on the way down. And then human grabs them back out. But it's slightly, this one is slightly negatively buoyant, so it profiles slowly, so you can average over these away focusing near the surface, and you can get to the surface rapidly. This one goes really fast, so it stays very still breadth in terms of its still, but you have to have its main profile to get good values, because you're gonna see wave focusing different things. Yeah, so they're deployed from the boat. Again, what you're doing is you to extract, so you have all the measurements in different depth, and to get a reflectance, you have to extrapolate it to the surface from your first measurement using a K that you derive along the way. It's quite similar to the other. There's a bounding process. But so everything I'm talking about is reflectance. I'm not talking about how you do case from these that was covered, and we can talk about it if you want more. Again, same issues as we talked before. There is some shading by the platform here, because it's a finite platform. That's the decider principle. We're disturbing the water while we're trying to get it. But again, if it's blue water, you're seeing a big volume. It's not as much of an effect. The more absorbing the water is, the worse it's shading on your vision. Because you're passing, if most of your light is gonna come close to this. But you collect it.
Then before you go, it's just worth commenting on the equation for KLU
Yes.
that you had in there. And that is to correct the variation over radiation for measurement at one depth at one time, and then your measurement deeper in the water column at a different time.
Excellent.
So you need to have that in there. That's there.
Excellent. So with this, you can do measurements in times where it's not perfect conditions, because you can adjust it with cloud passing, you can adjust for expansion. You don't have to throw the data out, you can adjust for expansion. This is not done by the hypernav because we don't have a reference at the surface. There's no reference buoy at the surface. So the only times where you get good data is when these are the same, because you do not have this ED at the surface. You actually, I should have not put this in because you don't have it. So the assumption is that there's no change in the irradiance. So of course it works in only very sunny, beautiful day, but these are the days where you do matchups. So hopefully that's not an issue, and hopefully you'll be able, by screening your profile, to say, look, my profile is changing in ways that it should not, and therefore I suspect as cloud, this data is not quality to measure. And that's the downside of this system, is we do not have 8 centimeters inside. Yeah, but the thing is, you cannot average something that biases the measurement. I mean, you can average it, but it's still very defined. Well, then, so when you get, how about having also floating with the hour at the same time? When we deploy these, they go out for a month and they drift wherever they drift. I mean, we're trying to control the drift by parking them at depth that will keep them in the same area. That's how. And by the way, all this data from HyperNav is available online of all the deployment we've done to date. And every time it comes to the surface of one that's in the water, you can get the data. It's completely open. All this data, it's not hidden. So here's another
system developed by Jean Pigny. Jean Pigny said, you know, there's all this assumption about crossing the interface, all this stuff here. How about I make the measurement above water? But I don't want to make a measurement that's affected by winds. Of skylight, which I'll show you in another system. So I'm going to have this code on the radiometer, and that will limit and that code is wide enough relative to the acceptance angle of the radiometer, the half angle of the radiometer, that I'm going to look only at water. I'm not looking at my sides, and this way I can measure what's coming straight out of the water. Which is an ingenious, when you think about it, it gives you straight the definition you want. But why don't you take me see this? There's shadow, and so the next paper they published about the shadowing, how to do a correction for the sun, from shading by the platform. Absolutely. What else can And by the way, we have a setup like this that we built. We might not use it in the lab this afternoon, but if you wanted to measurement like this, you can. We have a, yeah. Biofilm, but those will be also here. I mean, unless you think this will produce or contemplate biofilm, biofilm will also as well.
Sensor base.
It will be, it's very hard to keep the sensor base from getting wet. Unless it's flat column, unless you work in play or you work in a day like today here, it's very hard to keep the sensor from getting wet. And it gets wet, those drops that form the focus light, so those will introduce no limits. This is an ingenious idea, but as conservation of nature develops, it was still there's still the problem that I have something that could get wet, and if it gets wet, and the drop dries and the salt deposits, if they don't dry, they go to slide, so it's not easy. But in lakes, it can work really, really well. You use the lakes, and
I'll talk a little bit about doing this with an imaging radiometer. Much further away, you have to take only the pixels that are they're down in your tube. And I want to be
super. So here is this issue. So now, before I get there, another system, and that's a system we're gonna have on the boat when we go out, and you're gonna play with it today. You're gonna do these kind of measurements. That's an approach that it's an approach that Ken Carter really dependent, but Moby did the calculations. And the idea is as follows: I'm taking a radiometer and I'm looking at the water. And I know some of what's coming in is glint. So I'm looking down, there's glint as well as water leaving radiance that's coming into this sensor. Now, the glint, if I don't look straight at the plane of the sun, but I look away, the glint is going to be skyline. So I will also measure skyline. So I know the spectrum that this glint should have. And then I also measure ED plus for the normalize. And the idea is then I'm having, what I want is LW, the part that comes from within the water. For this, I have to correct for the glints, for this, for what's coming out. And I'll assume that this glint is some fraction of the sun. When I multiply the skyline by factor, which is what I'm going to do. That's the classic correction. There's no more involved correction. And that factor, this is the effective Fresnel reflective. Often, if you're looking at one, so the recipe typically, I have the sun in my back, 135, either right or left, 40 degrees. This is what I'm going to use because that's the one where the Fresnel reflectance is the least, and the least varying according to Mobley on the order of 2.8%. But this will change with wind. This is with viewing 90 angle, one thing that's going to change. So we typically use 40, but then as wind increases, that's his change. But again, in 40, it's rather stable compared to other angles. So this is why this has been chosen as the angle of the
wind effect is relatively small. And there's now correction also for polarization that came in later paper. So because near the surface, polarization can affect your scalar measurements. Now, I talked about ED as being collected by this, by a radiometer that's a planar irradiance meter, but you can collect it also with a radiometer that measures radiance if you put a plaque in front of it of known reflectivity and known reflecting property. So this is the reflectivity of the plaque. This is what you're measuring. This is pi is if it's Lambertian. If it's Lambertian, it's simply pi times what you're measuring divided by the reflectivity to tell you the ED that was there. And we'll do it today. We have a plaque, we have a white plaque, and you measure on the white plaque and you measure these and we'll compare the two. Now, we'll also use for yes.
Sorry to interrupt, but just going
Please
to
do.
the last slide.
Yes.
The angle of which you have,
Yeah.
Said it's like 40 degrees.
40 degrees to nadir.
Why 40 degrees?
Because as you see, it's the least sensitive to surface effects about wave.
Awesome. Thank you.
No problem.
But if you're in a very non-windy place.
Yeah, then you want to know if it.
Reach on it.
Yeah, okay.
And it's important to know that's the contribution of blend and sky reflection, right? So,
Yes.
you know, if you're looking at 70 degrees, you're not seeing any blend, but the horizon is so bright, you're seeing lots of white. There's one for this guy. Whereas when it's near zero.
And this does not take into account the direction of the wind that raising these waves. But you can think about it, it's not the same. 135, if the wind is blowing in this way, I'm not. There's no way. But there's a component that's also the directionality, but it was not entered into these computations, but you can see by eye that there's a difference whether you're looking at direction the wind versus in an angle to it. All the beautiful complications. So there's also something called an irradiance reflectance. We currently do not measure it, but it's important for you to know because it's in the literature. And one of the beauty of these is that, so it's measuring with an irradiance meter both up and down. One of the beauty of these is that you can use the same instrument. So you have no calibration as the measurements. What the reason it's not in vogue today is because that's not what the sun finds. It's not close to what the sun finds. And there's a few papers by Mopi showing that this is a little less good of an AOP than the other reflectants, the radiance reflectants, but they're quite similar. But it's really the fact that we cannot do anything to other side, as far as I can tell. And calling this beautiful paper from the thesis in 1989, doing these measurements hyperspectral with a light core and working out the first inversion, get phytoplankton absorption, phenol and absorption, and all those conditions. And they're not that different from what we mentioned today. And we're using the same approaches. So just so you know. And now the last one, because we all love it, the second. Second is also an AOP, weakly affected by sky conditions. It's weakly affected, and one can show it. Basically what you're looking at is that you're lowering a disk until you cannot see it anymore, and then you bring it back and they tell you, don't put it on the sun side. But the changes due to our vision are small, and it's a quite solid AOP, not only this, AOP. We have data going back to the 19th century. So if you want to understand science, this is still the way a lot of people do. It's extremely cheap. You don't have to send it to calibrate for thousands of dollars. So bring one with you. It's better than not having it. And yes, it's at the depth. I mean, what wavelength are we measuring? With the second? say what I did most sensitive to, anybody else, what do you think? What about the properties of the water? In a blue ocean, it's gonna be more affected by blue wavelength. In a coastal, it might be more green. Because it also depends on what light penetrates to the properties and come back to us. So it's a mixture of the eye response to the properties of the water, yes.
I made one that I covered with different colors of mylar film. So they were green, blue, red, and green, as well as black and white. And then you could see when any one of those colors turned black, that's when you lost that color from light. You could actually turn it into a spectral K meter by doing that. A lot of them.
So the original theory, and there's a lot of it, was that the attenuation down is a K function. While when it comes back, because it comes only from the disk, it's a beam attenuation line. K down and C up. Jumping V is a newer theory that claims that basically it's K's both ways. That's something for you guys to, for your generation to decide this battle. It's a fun battle to think of. So parting words, AOPs are very useful quantity to obtain BGC information regarding the ocean. So they're tremendously useful. They're necessary to reconstruct the subsurface slide film. So if you have only measurement of the surface and you want to know how it's distributed in the water, you need those. And they're also necessary to validate measurements done from satellite pushing. So they're important. How you get them and how hard it is to measure them, that's part of what you're going to do in the lab. Thank you.
Five to 11, so say
11:05.
11:10.
11:05.
Come back.
No, it's